I'm grateful to your neighbors for giving me this opportunity to make my presentation today. A preprint of the same title as today's talk is already available in archive. Okay. Well, let's dive into the topic. Let me explain the abstract. Two main theorems will appear in today's talk. First one is a syntactic description of finite monads on locally finitely presentable categories. There is a famous correspondence between algebraic theories and finite monads on sets. Our first main theorem generalizes this correspondence from sets to arbitrary LFT category. LFT is locally finitely presentable. Here we will define a new algebraic concept relative to A. This is called A relative algebraic theory. This is defined by a partial forms theory. Okay, next. The second main theorem is generalized Birkhoff theorem. Birkhoff theorem is a fundamental theorem for classical algebraic theory. The second main theorem generalizes to our relative algebraic theory. The first two parts explain some background and basic concepts. And the two main theorems will be introduced in third and fourth parts. Okay, let's start by talking about finite monads and algebraic theories. A single-sorted algebraic theory is a set of operation omega and a set E of equations. And note that each operation omega is assigned to a natural number called its arity. Arity represents the number of inputs of each operator. When a single-sorted algebraic theory is given, we can define the concept of models. Model is a set A where each operator omega is interpreted as an appropriate mapping which satisfies the all given equations. A typical example of models, typical example of algebraic theory is the theory of groups or the theory of rings. Then these models are groups or rings in usual sense. Algebraic theories are main subjects of research in universal algebra. Algebraic theories are closely related to finite monads on the category of sets. Categories of models of algebraic theories can be characterized as finite monadic categories over set. Roughly speaking, single-sorted algebraic theory equals finite monads on set. This is an important slogan throughout today's talk. Several generalizations of this slogan are known. When a set of sort S is given, then S-sorted algebraic theory corresponds to finite monads on S power of set. Furthermore, we can define the ordered algebraic theories. Those correspond to finite monads on the category of coset. Surprisingly, a detailed version of third correspondence is a recent result. This is a result by academic called Schrader in 2021. In today's talk, we will generalize these such correspondences from concrete categories to arbitrary, locally, finally presentable categories. Okay, in the next part, we will give a brief description of LFT categories and partial form theory. The definition of LFT category is here. However, we will not go deep into the definition of LFT categories in this talk, so the audience can skip this definition. To say more, there is nothing wrong with mosaic like this. The only important thing is there is a purely categorical sentence here. It is known that LFT categories are characterized as categories of models of various kinds of logical theory, such as Cartesian theories, or essentially algebraic theories, or partial form theories. Of these, partial form theories will play an important role in today's talk. Let me explain the idea of partial form theory. Since this is a category theory conference, so let us now define a category. A small category consists of a set of objects and a set of morphisms and three functions representing identities, domains and codomains, and a partial function representing composition of morphisms. We can define the theory of small categories as a partial form theory. Then, each small category is a model of the theory. Roughly speaking, partial form theory is a logical theory which can deal with partial functions. Now we will give a brief introduction to partial theory. First, multi-socket signature is pair of set of sources, a set of function symbols, and a set of relation symbols. Note that each symbols are assigned to its identity, shown here. And then, as in ordinary first-order logic, the notion of terms and formula and context are defined. Here, today we will only deal with form formulas, which are finite conjunctions of atomic formula. The definition of partial theory is very simple. A partial form theory is a set of form sequence. Here, a form sequence is a pair of form formulas denoted in this way. This informally implies means that phi implies psi. Okay, now the definition of partial form theory up to this point is actually no difference from the definition of ordinary form theory. So, what is the difference between form theory and partial form theory? The difference lies in the concept of models. This table shows the difference between form theory and partial form theory. Both theory is a set of form sequence, and the interpretation of relation symbols are same, but interpretation of function symbols are different. In ordinary form theory, each function symbol is interpreted as a total mapping, while in partial form theory, each function symbol is interpreted as a partial map. validity of phi is Variety of phi means that all terms in phi are defined and phi holds. This is because each term interpreted as a partial mapping in partial theory. In particular, for a given term tau, the equation tau equal tau means that its interpretation has a value. So we will use this abbreviation. You can read this. Tau is defined. For partial theory T, the category of models of T is denoted in this way: T mod. And then, as introduced earlier, partial theories characterize LFT categories in this sense. A typical example of partial theory is the theory of small categories. Let us consider two thoughts representing objects and morphism, and let us consider four function symbols representing identity, domain, codomain, and composition of morphisms. And then we can define theory of small categories. It consists of, for example, ID is total, and B and C are total. The composition ZF is defined if and only if BZ equals CF, and so on. We can check that a model of dispersion theory is precisely a small category. Okay, now that we are ready, in the next part, we will introduce the first main theorem. Throughout this part, we fix the partial theory S over S sorted signature sigma. Now we present a new algebraic concept relative to S. Here the symbol K represents me. My last name is Kawase. S relative signature is a set omega of operations where each element is assigned to a whole formula called its arity and assigned to a sort which called I. You can consider each element omega as an operation, and you can consider arity as domain and type as codomain. More precisely, each small omega is a partial operation which outputs a result of its type if and only if the input satisfies the formula of its arity. When S relative signature omega is given, we can obtain a new signature sigma plus omega by adding each element of omega to sigma as function symbols. A consequence over sigma plus omega is called an S relative judgment if its precondition contains no symbol from omega. And a logical theory which has S relative judgments as its actions is called an S relative algebraic theory. That is, an S relative algebraic theory is a pair of an S relative judgment, S relative signature omega, and a set E of S relative judgments. Let us define the concept of models of S relative algebraic theory. For a given S relative signature, its algebra is a model of S with the interpretation assigned to each operation. Here, the interpretation of each operation is a partial mapping, which outputs a result of its type if and only if the input satisfies formula of its arity. as explained earlier. A model of an accelerated algebraic theory is its algebra which satisfies all given accelerative judgments. And then the category of models of a given relative algebra theory is noted like this. Algae omega E. Let us now compare ordinary multi-sorted algebraic theory with relative algebraic theory. Multi-sorted algebraic theory take setless as its base category, and each operator take a finite tuple as input, and we can use equation as its action. On the other hand, accelerative algebraic theory take SP mod as its base category, and each operator takes finite tuple which is satisfying Hom formula phi as input, and we can use accelerative judgment as its action. Most algebraic theories have three forgetful adjunctions like this. Okay, now there are two important points about relative algebraic theories. First, each operation is not to be total, but its domain must not contain any operator from omega. So that is, its domain must be defined by S language. Second, we can use implication as actions. But its precondition does not contain any operator from omega. That is, preconditions must be written in S language. If you understand these 3 points, you are a master of relative algebraic theory. Okay. Accelerative algebraic theories you have here are in a sense equivalent to finite monads from SP mod. That is, finite monadic category over SP mod characterize category of models of accelerative algebraic theory. This is the first main theorem in today's talk. Roughly speaking, this theorem asserts that accelerative algebraic theory is equal to finite monads of SP mod. This is a generalization of classical one. Since arbitrary LP categories is represented by SP mod for some S, we will have explained finite monads over arbitrary LP categories. So when LP category A is given and it is equivalent to SP mod, then we may use the word A relative algebraic theories instead of S relative algebraic theory. By the way, it is known that the category of small category is finite monadic over the category of quivers or directed graphs. We present another proof of this. First, we define a pattern theory of quivers. This theory has two sorts representing edge and vertex, and this theory has two total function symbols representing source and target. Then we can define S-squared relative algebraic theory of small categories. Its definition is here. Oh no, there are so many symbols. It looks very complicated, but no problem. Important points are only two. First, the domain of all operations are written in quivers language. And second, precondition of action are also written in Kuiper's language. So this is Kuiper relative algebraic theory. Since Kuiper relative algebraic theory is equivalent to finite monads on Kuiper, so this finishes the proof. Now, this is the last part. Here we present the second main theorem. One of fundamental settlements in classical algebraic theory is Birkhoff's varieties theorem. Let omega E be a single-sorted algebraic theory, and let E be the full subcategory of it, the category of its algebra. And then this theorem asserts that the full sum E is definable by adding equations if and only if it is closed under products, sub-objects, and surjective images. This class E is called Birkhoff subcategories in previous talk. This theorem is also called HSP theorem. It is known that the Birkhoff theorem can be generalized to the multi-sorted case. In this case, however, filtered coordinates are added to the closeness constant. Now, the following will be of interest. Is it possible to generalize Birkhoff theorem to our relative algebraic theories? In the case of relative algebraic theories, a full subcategory defined by relative judgments is closed under products and filtered coordinates. On the other hand, it is not closed under surjective images nor sub-objects in general. So we will modify them in this way. We will modify surjections to U attractions and sub-objects to sigma closed sub-objects. Then we obtain a generalization of Birkhoff theorem to relative algebraic theory. Let omega E be an associative algebraic theory, and let E be a full subcategory of the category of its algebras. And then the full sub E is definable by adding associative judgments if and only if it is closed under products, sigma closed sub-objects, U attracts, and filtered coordinates. This is the second main theorem in today's talk. And this generalizes existing Birkhoff theorem in the following sense. For example, letting S be the theory of the set, then we get the original version of Birkhoff theorem. And next, letting S be the theory of S-sorted sets, and then we get the S-sorted version of Birkhoff's theorem. Furthermore, letting S be the theory of cosets, and then we get Birkhoff's theorem for ordered algebras. By the way, we haven't yet mentioned the definitions of U attracts and sigma closed subjects, so in the meantime, we give a brief introduction of this. The definition of U attraction is very simple. For a given factor U, a morphism P is called U attraction if UP is a retraction. In our Birkhoff theorem, we take U as the projective factor. Next, let us consider, let us define those sub-objects. Here we fix arbitrary Horn theory T and consider the category of models of T. a subobject is called T-cross or sigma cross if the following diagrams form products for any symbols. That is, closeness means that all structures of A are induced from those of B. Now, we present an example of closed subobjects. Let us consider the partial theory of monoids denoted by T1. This theory is single-socket and has a constant symbol and total binary operator. This theorem contains the usual identity actions and usual associativity actions. Then, the inclusion from natural numbers to integers as additive monoids is T1 closed. We can easily check this. By the way, there exists another partial theory of monoids denoted by T-1. This theory has a partial inverse operation in addition to the usual monoid operators. This new operation sends each invertible element to its inverse. It is easy to verify that the category of models of T-1 is isomorphic to the category of monoids. Then the inclusion from N to Z is not T-1 closed. This is because that this inclusion is not closed under additive inverse. Therefore, T-closeness is not a categorical property, but depends on how we take the syntax T. So, this is just like so. In the co-closeness condition of our theorem, only the sigma cross subobject depends on the choice of partial theory S. This is a notable feature of our theorem. While in the original version of Birkhoff theorem, all the closeness condition is independent of syntax. Now, my presentation is finished. Thank you very much for your attention.
Short question. Okay. Please.
It's a comment. You're probably already aware, but there was an old paper by Dana Scott on identity and existence in intuitionistic logic. It appeared in which talks about when presenting theories for partial with the notion of partiality, and I believe it may be useful for your axioms. I'll tell you later.
I think that's
again. It's a comment.
yeah.
There is an old paper by Dana Scott in application of sheaves. It appeared in 1977. And on identity and existence in intuitionistic logic. And I believe it may help you in presenting the partial theories.
Are you using this theorem is formally or
No, I'm not saying that. No, this is very interesting, and I'm very pleased with your talk. No, it's just a comment. And I was making it quick because it's over time already.
Please discuss.
Yeah. So, first little remark, terminological. When you say quiver or directed graph,
Why?
you said huh?
There's two names for the same notion.
No.
Just
no.
Without saying things.
Yes, I know you mean the same thing. But there are two things. In category theory, what you call quiver is what we call just graphs. Now, when you say directed graph, we are now afraid. Do you mean the same thing, or do you mean directed graph in the sense of graph theory, which is different? So I think it is safe to call them just graphs and say you're calling them graph as category theorists. Or if you speak to people who do not like category theory, just call them quivers and don't mention graph at all. But apart from this, I have a serious question with this theorem 2. This one, yes. When we do ordinary Birkhoff theorem, there are adjoint factors between variety and subvariety. Yes, here I don't think there is adjoint factors, but did you study the situation when you have them? In your E, included in algebra, it doesn't seem to be reflective subcategory, does it?
This is reflected. If these conditions hold, then this inclusion is reflected.
It is reflected.
Yes.
All right.
Other questions for the coffee break?